Good day and welcome to the third video in the series of EBN tutorial videos. In this video, there's only one new concept that you have never seen before. But other than that, everything else you should have seen in high school physics. So, first things first, we're gonna start off with Ohm's law, right? So Ohm's law is the classical V is equal to IR. The voltage is equal to the current going through the resistor multiplied by the resistance of the resistor, right? And the inverse of resistance is conductance. That's something also you might not have known, but it's pretty intuitive. There's nothing actually new going on there, right? So the one thing about wires, when you're doing EBN and all the way up until about fourth year, is that you consider your wires to have zero resistance. Now the resistance of wires is not really zero, but it's so low compared to the values of your resistor and your other components that assuming that it is zero does not give you massive errors, right? Okay. So, and on the opposite spectrum of that argument, when you have an open circuit, that means that your resistance is infinite because there is no current that can jump across from this point to that point. It is, I won't say it's impossible, but it is very, very unlikely. The reason why I say it's not impossible is because, everybody knows of the classical lightning storm, right? There actually is a conductor. Air is a good conductor. Okay, air is not a good conductor, but it is a conductor. So it is possible if you generate enough current and enough voltage across the two that a current and a voltage can be generated. But in EBN and all the way till fourth year, actually all the way till ad infinitum, you do assume that if there's an open circuit that there is an infinite resistance, right? So yeah, short circuit resistance is zero, open circuit resistance is infinite. Those are not new concepts. This is just high school stuff. And then the next thing we cover are branches and nodes. So nodes are areas that are all connected to the same corner, same node. So this would be a node, right? Because there's a connection there, there's a connection there, there's a connection there, there's a connection there. That's one node. Why it's called a node, you will find out in chapter 3 when we do nodal analysis and we do mesh analysis. That's when real EBN starts and we stop doing this boring high school stuff, right? And then on the opposite side of a node is your branch, right? So your branch is a single element. So that's a branch, 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 right? So those are your branches. That's the difference between a branch and a node. And then we get to Kirchhoff's two laws. His current law and his voltage law. This again is basic stuff like your KVL and KCL, right? So Kirchhoff's current law states that the sum of currents entering a node is zero. And Kirchhoff's voltage law states that the algebraic sum of all voltages across a closed path is zero. Let me show you what this means with the previous slide, right? So, let us concentrate on the loop that has our voltage source here, right? I'm gonna redraw that. That's a 10V. That's a 5. That's a 2. Right. So when we're considering this node, we say that the sum of voltages here is equal to 0, right? So if we say that this is V1 and that's V2, right? So therefore 10 volts plus V1 plus V2 is equal to 0. That's basically what this says. It says that, okay, actually I may have written it the wrong way. This is supposed to be 10 is equal to V1 plus V2. My bad. I got my signs mixed up. So this basically means that this 10 volts is distributed between this component and that component. That is what KVL basically states. This is, again, nothing new. Right. Should probably use a bigger eraser. So now to demonstrate KCL, we are gonna look at branch B. Branch B looks like a good branch. We're gonna look at this branch, right? Okay. So what we know from our Kirchhoff's voltage law is that the sum of, Kirchhoff's current law. Kirchhoff's current law is that the sum of currents entering a node is equal to the sum of currents leaving a node, right? So obviously, because here there's a voltage source and a resistor, there is a current entering there, right? And here, as you can see, this is a current source. This is another current going into here, right? So this means the sum of current 1, this is current 1, and current 2, is going to split between here and here, right? The way it's going to split is dependent on the current division law, right? So let's say I'm gonna call current 1 and current 2, the sum of it equal to IT. So I1 plus I2 is equal to I total, right? So I'm pretty sure that you know how current splits up between resistors. The same way there's voltage division, there's current division, right? So for here, we're gonna look at green. This is gonna be I'll just call it I4 and I5, right? And this is the 3 ohm and that's the 2 ohm. So I4 is equal to the 3 ohm divided by 2 plus 3 I total. And I5 is equal to the 2 ohm over 2 plus 3 multiplied by I total. This is simply your current division. This is not, I'm assuming this is not a new concept, because this is something that, in high school you did do parallel and series circuits. So this is not something new, but yeah, this is basically how current splits up between parallel branches, right? And yeah, that's basically it. And since we're looking at the splitting of current between branches, we might as well as look at the voltage at branches, right? So something else that you should remember is that the voltage here, we'll call that V3, is equal to the voltage there. Man, yellow is a terrible color. Why is yellow so bright? Oh, we'll go for blue. So that will be V3 is equal to the voltage there, V4, which is equal to the voltage there, V5, right? That is because all three of them are in parallel, right? So the voltage here across the 2 ohm is equal to the voltage across the 3 ohm, which is equal to the voltage across the 2 amp source, because they are all in parallel. And yeah, that's those are the two things about parallel. And the one thing about series, I guess I might as well write it in here. This is getting a little bit messy. Sorry for that. I didn't plan for it to all just squeeze onto this page. So for that branch, the voltage, because that's V3, we'll call this V4 there, and V5. Wait, actually no, that's V3. My bad. V3. So the voltage V4 is equal to 5 over 2 plus 5 multiplied by our source of 10 volts. And our voltage V3 is equal to 2 over 2 plus 5 multiplied by 10. That is the voltage division of a series circuit. So yeah, that's some basic stuff. Nothing new is going on here. And sorry for like trying to just fit it all onto one page. I just got carried away. And yeah, nothing new really happening there. Oh yeah, adding up sources, right? So when you have parallel current sources, you can add them up, right? So if you had a resistor here, or a resistor there, or even there, it does not matter, because these three current sources are in parallel. So therefore, you can do this even if you had these 3 extra elements. That is something that some people it just misses them. So that's something pretty cool. What else when you cannot do this would be if you had, for example, a resistor here or a resistor there. Yeah, right. So now, because this source, your current source here has one node there and one node there, it is not in parallel to this second current source here, which has one node there and another node there. As you can see, this node here is there and your bottom node is there. So therefore, these two current sources are not in parallel because they're not connected to the same 2 nodes. So when you have a resistor in series with your current source, you cannot say that they are in parallel, right? Only when the resistor is in parallel with your current source can you do the step right here. Yeah, that's also something you should watch out for. And series resistors, series voltage sources. You can only add up voltage sources when they are in series. So the next concept we are going to cover is series resistance and parallel resistance. So when resistors are in series, you simply just add them up. So if you had, resistor on. So you got R1 there, you got R2 there, connected, and you got R3 there, and you're told to find the total resistance between A and B. It is simply an addition of R1, R2, and R3, right? And the voltage division, as I was speaking about early in the earlier verb, as I was speaking earlier in the video, your voltage division is denoted by this equation, right? So the resistor you're looking at divided by the sum of resistors in the loop. That is how you find the voltage across a specific resistor. Yes, awesomeness. And then there is parallel, right? Parallel is parallel. So when you had your R1 there and you had your R2 there, the equivalent resistance is denoted by this. 1 over R equivalent is equal to 1 over R1 plus 1 over R2. You pull out your magical Casio FX991ZA plus, and you type that into your calculator, and then you invert the result, and that's your equivalent resistance. But usually you've got about 2 resistors in parallel. They don't really like to give you too many resistors in parallel, so this is the one you use. And a quick tip, right? Let's say you had R1 with R1 is equal to R2, right? So the equivalent resistance here is equal to half of your of the equal resistance. So because these are 5, your R equivalent is 2.5. You can take out your calculator and test it out. But basically, okay, 5 times 5 is 25, divided by 5 plus 5, which is 10, which is 2.5, which is half, right? This is a quick tip for like when you're in the middle of something, things are getting rough, and you're running out of time. Then you just see 2 resistors in parallel that are equal to each other. Just remember that the equivalent resistance is equal to half. Yes. Oh, okay, yeah. If you've got a bunch of resistors, this is the formula you use. Yeah. And this is as I was saying, right? But I gave you the unique case where there were only 2 resistors in parallel. So if you've got, let's say, 10, let's say, for example, you have 10 ohm resistors, right, in parallel, right? All of them are 10 ohms, right? So using this formula, you would realize that your equivalent resistance is a 1 ohm resistor. It should probably 1 ohmy. So yeah, this is a nice formula to remember. R equivalent is equal to R over N if your resistors are equivalent. Yes, awesomeness. Parallel resistors and current division. We actually already covered this in the earlier video. Yeah. So this is the one and only new concept that you will be encountering in chapter 2. This is your Wye-Delta transformation, and I absolutely hate them. They are only useful in EBN. I have not encountered them in my years of studying, but yeah, this is something that you just have to know, right? So your delta is this guy outside here. As you can see, a triangle. If you think about derivatives, delta y over delta x, that's why it's called a delta. Instead of calling it a delta, you can also call it a pi. Right? If you think about it, if we do that, stylus is dying. that does that's a very shabby pie, but like, yeah, it's also called a pie, just for, just for interest sake. And yeah, here, there, this is just memorization of formulas. There's nothing really to say about this but this, right? When you're going from, when you're trying to find your, let's say for example, RA, to try to make these formulas easier for you, right? We are gonna be looking at this one, right? You can see RA is R1, R2, R2, R3, R3, R1. You can see that is just the multiplication of everything together divided by the one that it is opposite, right? R1. Let's look at RB. RB, which is this one, it's divided by the opposite one, R2. RC, which is this one, is divided by the opposite one, R3. And that's a quick way for you to remember these formulas. So now, as long as you can memorize one of those formulas, you can get the other three formulas. That's something very nice. Okay. And when you're going to your Y, let's look at R1, right? So you can see R1, the opposite to R1 is RA. So basically, you multiply the two that are not opposite, RB, RC, and you add the rest together, right? R2, which is here, the opposite of it is RB. You can see this is RC, RA divided by the sum of the rest, and R3, the same thing. So when it comes to this, you just need to memorize a formula for RA, a formula for R1, be able to sketch this guy quickly without blowing a brain cell or two, and yeah, right? But the more and more you start doing past papers and start practicing these things, you are going to realize that the questions you come across, your resistors are going to be equal, right? So therefore, usually it's good enough to memorize this formula. Like, let's say this is the last night. You studying like the night before your semester test or your exam, and like you trying your best to try to memorize how to remember these formulas, and it's just not getting in. Save yourself some effort. And just remember this. I'm not saying this is the only version of the formula you use. I'm saying this is the most important version of the formula you use. So it's better to know this one off by heart than to try to memorize this one if and only if you are short of time. But if you have the time, please memorize how to draw this and memorize these formulas. But if it's a do or die situation, it's 5 minutes before the test, and you just realize you don't know R delta Y, then just remember this formula. And that seems to be the end of this video.